everyone. This is the part 2 video to MA162 Exam 1 for Spring 2022. For question 7, we're given two functions revolving around the y-axis. So usually for y-axis revolutions, I will like to use cylindrical shells, but we'll see in this situation which one to use between washers and cylindrical shells. So just a regular parabola, probably to make that better. Something like this, where this area is revolved this way, right? So we have something like this area over here. Right, so we can see that if we use cylindrical shells, since it's about the y-axis, we can see that the radius of the cylindrical shells is just how far away it is from the center, which is the y-axis, right? And that is just x. Whatever that radius at that point is just x. And the height of that cylindrical shell, right, is the top line minus the bottom line, which would be the line minus the parabola. So let's just plug that all in. So we have, oh, we need to find the bounds too. So just putting them together and solving them, right? So we have x equal to 0, 1. So cylindrical shells, 2 pi RH, right? R is just x, as we talked about. H is the top function minus the bottom function. And we are doing dx, since all the variables we're using are x. So here, bring the 2 pi outside, and right, simplifying things, x squared minus x cubed, 2 pi times, that would be x cubed over 3 minus x to the 4th over 4, evaluated from 0 to 1, so 2 pi times, that'd be 1/3 minus a 4th, so 1 over 12, and then minus 0 plus 0, doesn't matter that much, we have pi over 6. Right, answer choice E. So gotta remember your pi. Right, these answers are just hoping that you forgot the pi on the cylindrical shell equation. For number 8, if we read the question, right, it's y equal to square root of cosine x, and it's from negative 2 pi over 2 to pi over 2, and it's sort of like there's shapes coming out of the graph, and if you recall, this is very similar to the last exam's number 7, right? This is fall 2021, number 7, where same function, same bounds, all the wording are exactly the same except for this time it's, instead of isosceles right triangle, right, it's squares. So it's we will approach this exactly the same way, so except for the area part. So being like an isosceles triangle, it would be squares. But we can look at the graph, right? This is, so just imagine this is sort of a triangle here. It's just a square, and this is the graph that we need, the cosine, square root of cosine graph. Right. So first, let's graph this. So the cosine looked something like this. Right, it doesn't really matter if you can get exactly what the graph looks like. You just have to sort of guess what cosine of the square root of cosine is. If you don't know what that is, that's completely fine, right? Cosine is, right, it starts at 1, it does something like that, right? And when you square root this, right, of course, negatives doesn't make sense, but we only consider from negative pi over 2 to pi over 2, which is the positive part, so it'd just be like shorter compared to the original cosine graph. But nonetheless, so we have negative pi over 2 to pi over 2, and whose cross-section through the solid is perpendicular, so we can imagine they're like these little squares that comes up, right? And the length matches the y value here, right? So throughout there's all these squares. So these squares, we can say that they're basically slabs in a sense, right? With really thin uh, sort of the thickness uh, dimension, right? We can say that these these lengths can label the two lengths that are not very thin are cosine x, or rather square root of cosine x, right? And then the the thin part is dx. It's we're imagine it to be super duper thin, and so the total volume of the single slab would be um, cosine x times cosine x times dx, right? It's just all three sides times to each other. So once we have a single slab, we can then write an integral to sum them all up, right? We have from negative pi over 2 to pi over 2, and then we have, actually, um, let's consider using a different bounds. 2 times 0 from pi over 2, because it's symmetrical. This side has the same volume that this side, as it is a even function. And so it will be square roots uh, times each other. It will just be cosine x dx. And then solving this simple integral here, just sine x from 0 to pi over 2 times 2. Plug in pi over 2, and that would be 1 minus 0, and that would be 2. Right, sometimes I'm cautious about pi over 2 to 2, negative pi over 2 to pi over 2 bounds, because sometimes you might get something like, cosine pi over 2, which is 0, and then cosine of negative pi over 2 is also 0. So sometimes you might end up with 0 minus 0, which doesn't really make sense. And in this case, since you have sine, it would be, if we did pi over 2 and negative pi over 2, it will be 1 minus negative 1, which will give us the same answer as being 2. So that's just something that you might want to look out for. If you somehow your volume equal to 0, what you could do is just split the two parts up, and then 2 times like whatever from 0 to pi over 2 instead of negative pi over 2 to pi over 2. For question 9, we're given y equal to sine x with x bounded from 0 to pi, and that is revolved around y equal to -1. So first, draw it. Right, we have sine, which starts from 0, 0, going to pi, which ends here back at 0. And this line, let's see, and it's bounded by the x-axis. Right, revolves around -1. That's not drawn to scale, but that's fine. So revolved around here, right, something like that. So with this, we can use the and washer method. You can see that really the distance right between like this point and the revolution line is like from the top equation down to -1, and the x-axis, which is y equal to 0 to -1. So we can then write the integral limit of integration is just 0 to pi, and what dishwasher start with pi, and then r1 squared minus r2 squared. So r1 squared would be the top function, sine squared x, minus, actually that needs to be +1 squared, because it's sine x being this line, and the distance between this line and this sinusoid away from the revolution line, which is -1, right? Minus the second line, which is 0, y equal to 0, minus -1, which is +1, right? The distance between the x-axis and the y equal to -1 line, right? All this is going to the dx, right? Every single little slice we're considering are going in the x direction. They are changing the x direction, so it's going in the x direction. So here, if we just ignore this 0, we'll see that this is just option A. For number 10, we have a surface area question. So first, let us write the surface area equation. Right, it's the integral of whatever bounds a and b, 2 pi times the equation. In this case, would be x cubed times the square root of 1 plus dy dx squared dx. Right, this part is from the arc length formula. That's a way to memorize that. So then, let's graph it over here. Right, generally cubic function looks a bit like this. Right, we just concerned with around this part, from 0 to 1. Right, and then since we need dy dx, let's just do it here. Dy dx, right, that'd just be 3x squared. So let's plug that all in. 0 to 1, 2 pi constants go outside, times x cubed is y, square root of 3x squared dx. So simplify a little. Notice we have 1 plus 9x to the 4th inside. So here, pretty complex integral at first, but you notice inside the square root is 1 plus 9x to the fourth. And if we take the derivative of that, we can get a um, x cubed outside, right? If we just look at it inside, and it will come up with a x cubed term. So we can use that with u sub. So if we make u equal to the inside of the square root, then du, just take the derivative of the other side too, we have 36x cubed dx, right? Since we have um, x cubed and dx here, I'm just going to move the 36 to the other side. 1 over 36 du equal to x cubed dx, right? So I can replace x cubed and dx with 1 over 36 du, and I can replace uh, the inside of the square root with u. So let's do that. So we have 2 pi. Right now I'm not going to consider, I'm not going to bother with the limits of the integration yet, since we are now moving with u. So square root still remains, square root of u, and then it would be 1 over 36 du. I can move the 1 over 36 outside, make it pi over 18, and then this integral is much better, as this is just u of u to 1/2, and consider chain rule, we will just have a 2/3 u to 3 over 2 power. And now we can plug in u back in here, since the integral is solved. Or yeah, so we have, let's say, it would be was, and now I can put the limits back in from 0 to 1. I can move the constants all outside. It would be pi over 27. 2 cancels out with a 2 there. And now plug 0 and 1 in. Right, we have, if we plug 1 in, it will be 1 times 9. 9 plus 1 is 10. So we have 10 to the third, 3 over 2, whatever that is. And then minus 0 in of 0 plus 1. 1 to any power is 1. So now that should be our answer, which is answer D. For number 11, we're again given a few functions, and we're asked to use cylindrical shells to solve for the volume. So first, let's graph it. So first, y equals 0 is just the x-axis, right? And then the quadratic, right? First, the quadratic has a negative term on the square, so it's a quadratic that opens downwards. And we think about the axis of symmetry. It's b over 2a, so actually it's negative b over 2a, so we have negative 1 over 2 times negative 1, that's a half. So we know that this function has a symmetry around half, and since we can usually you can see that it's 0, 0, 0, right? If you plug in 0 for x, you come up with 0 for y. So it goes through the origin, and then it goes up a little, and it goes back down. So this is like 1 over here, right? It's symmetrical around half, and looks something like that. And the rotation line is x unit -1, which is here, vertical line. Right, so we are bounded like this. Right, our bounds would be 0 and 1. Right, if you plug in 1, 1 minus 1 is 0, so it hits the x-axis as 1, 0 again. And we are using cylindrical shells when we flip around this way. So somewhere over here has something like this too. So we think about cylindrical shells, right? We have 2 pi RH. Right, what is R? R is the distance away from the rotation line. So for in this case, if our distance, let's say, is x on this part, right? That x has to be added, has to be calculated to the distance of x equal to -1. So we have x minus -1 will be the distance away from -1. So R will actually be just x plus 1. Right? It's 1 away from the origin, which then you count x. And then h is the height, which is just the top function minus the bottom function. And since the bottom function is y equals 0, you'll really need to consider the top function, which is just x minus x squared. So with all that sorted out, let's put in our bounds, put the constant outside, and we have x plus 1, x minus x squared dx will be our volume. Simplify inside, so we have x times x squared, plus x, minus x cubed, minus x squared. X squares cancel out, so our volume would be, let's see, do the integral, x squared over 2, minus x to the 4th over 4, evaluated at 1 to 0, 2 pi times 1/2 minus 1/4, so that'll be 1/4, right? And then it's minus 0 plus 0, so we have pi over 2, which is answer choice E. So at 12, we have an application of integrals, and this just deals with springs. So first of all, right, we write the spring constant, or force generated by a spring, right, is spring constant times the change of length from the natural length, right? So we don't have the spring constant here, so let's calculate it, right? We have 50 Newton, and we have the length is 1.5 meters minus 1 meter. All right, then we get the spring constant is 50 divided by 0.5, which is 100 Newton per meter. Right now, how much work is done, right? Work is the integral of force over the distance, right? In this case, I use dr, but it's dx, dy, or dz. It depends on whichever direction your force is going, right? So in this case, the work is from 2 to 3 and it would be force is spring constant times x, right? Dx x in this case is the same thing here as we have dx in the back. Right here, pretty simple. Plug in 100, and then we have soft integral 50x squared value from 2 to 3. Then that's 450 minus 200, which is 250 joules. Thank you for watching this video. The past exam archive and all the videos I did related to this exam will be linked in the description below. Please check them out if you're interested. Thank you.